Well, hello, friends. Today we're going to go over a little bit how the Serenity Windows Server works. Just a high-level overview, really. But yeah, so here it goes. This is just the state of things today in June 2019. If you're watching this, a year from now, probably it works very differently today. But let's look at the current state of things. So here's a little outline of the things that we're going to look at. I'm going to look at high-level architecture, just the big parts, what they are. Then we're going to talk about the display frame buffer, how that works, the keyboard input, how that works, mouse input, and then the server, the clients, the window manager, the compositor, and then we're going to talk a little bit about menus, how those work, and then we'll finish off with looking into the future, like what's coming next, what are some ideas I have for what to work on, improvements, stuff like that. So let's jump right into high-level architecture. So I sort of drew this little diagram here where we see the kernel and the user spaces separated, and the Windows server runs entirely in user space now. It used to be in the kernel, but now it's in the user space, and it communicates with the kernel through various means. So it's receiving data. We can see here. Can I get my cursor? Yeah. So it's strictly receiving keyboard input and mouse input from those drivers, but then it has sort of a bidirectional communication, if you will, with the display driver, because we have to also like read pixels in order to do alpha blending. But down here in user space is where all the compositing stuff and IPC action happens. So each client process manages its own bitmaps. There's one per window, and then they communicate back and forth with the Windows server, and then the Windows server here takes all of these window bitmaps and then composes them into a single screen bitmap, which is then blitted into the display frame buffer. Basically, that's basically how it works. Yeah, and then these clients, they talk to the Windows server over local domain sockets, but the bitmaps are in shared memory, and the bitmaps are owned both by the client and the Windows server. Anyways, that's just the high-level architecture. So let's just move forward into the next detail, and that would be the display frame buffer. So it's implemented as a kernel block device right now, and I've only implemented support for the box or QEMU VGA device. So this is like a pretend VGA card that does not exist in the real world, but it's convenient for testing and bring up because it implements the same feature set as a real card. It's just that it does things in its own way, and currently we're only targeting that. But the BXVGA device in Serenity, it has IO cuddles that you can call if you want to switch to video mode to like change the resolution, and we also have IO cuddles that we call to do page flipping. So the Windows server is double buffered, which means that when we're doing the compositing, we are rendering into one buffer while another buffer is on screen. And then when we are finished compositing and we're ready to show what we made, then we use the IO cuddle to do a page flip. And that IO cuddle is basically the Windows server telling the kernel that, hey, just flip the pages. And then it goes and talks to the VGA hardware to actually do the flip, which is a very short operation. And then one thing that I really like here is that the frame buffer is a block device, which means that you can mmap the whole thing, and then you have access to the raw 32-bit RGBA values. So they look like, that's what I tried to draw here at the bottom, which is just the red, green, blue, and then it's the alpha, but that's not really used, or that's not actually used in the frame buffer for the display. It's just laid out this way because it's really convenient to have 32 bits per pixel. Makes writing pixel manipulation code really, really easy. Yeah, so that's a little bit about the frame buffer. Let's go to the next thing. That would be the keyboard. So we have a keyboard device, which you can talk to on dev keyboard, and it's a character device, and you can read from it. That's the only thing you can do, really. And every time you read, you get one key event, which is a struct that's defined in the kernel. And every such event has the key code, and it has the Control, Shift, Alt, and logo button pressed or depressed states. And all of the modifiers and codes, you can find them in the kernel keycode.h. And what the Windows server does is that it just selects on dev keyboard, and then whenever there's something to read from there, we know that we have a key press or a key release. And the mouse works very similarly. It's currently we implement a PS2 mouse device in the kernel, and you can listen to it by hooking dev ps AUX, or I guess that stands for IBM PS2 auxiliary port. Maybe there should be a nicer name for this thing eventually, but that's what it's called right now. And it's also a character device, and every time you read it, you get a mouse packet, which is a struct defined also in the kernel. And each packet has the X, Y, and wheel deltas along with the button states. And just like the keyboard, the Windows server just selects on the dev ps aux, and it will read packets from it when they're available, and then process those as incoming mouse events. Okay, now the server part of the Windows server is a socket server that listens for local domain socket connections on the temp ws portal file socket. I don't know what you call it. you connect through that file, and anyone with write access to temp ws portal can connect to the server. So if you wanted to, you could set it up in such a way that like you make a group of users that can all talk to the Windows server, even though it's running under a specific user account. And root can also connect to the Windows server and run graphical apps on anyone's Windows server. And the server is driven by the WS event loop class, which is a subclass of C event loop. C event loop is in libcore, and C event loop is the base class for both WS event loop in the Windows server and the G event loop in the libGUI. So it's the base class of all event loops in Serenity. And the main loop driver in C event loop is basically a call to select that includes all of these different file descriptors that we care about. So the keyboard, the mouse, but also like every client that the Windows server. And basically the work that the event loop does, and the main work of the server, is turning all of that incoming data from all those devices and clients and turning them into WS event objects, which can then be dispatched to their respective listeners. Okay, so the clients. The clients, they connect to the local socket via the temp WS portal that I mentioned. Every client is represented by a WS client connection object in the Windows server. And what they do is that the client will send WS API client message structs. They just send those across the wire or across the socket, and the server will respond with a WS API server message. Although not every client message expects a server message in response. So it's like a little bit, you have to look at each message to see if there is a corresponding response message. Because the things that have a corresponding response message, you want to wait synchronously in the client until the response arrives before you proceed and do anything else. Whereas for certain messages, it doesn't really matter that much when the server acknowledges what happened. For instance, if you're just informing the server that like, hey, I would like to set my title to this, then maybe it's not super important that you hear back from the server. You can just like throw that message out there, and then the server will deal with it at its convenience. Anyway, so each client manages either 1 or 2 backing store bitmaps per window, and then it tells the Windows server which of those bitmaps to display for that window. And that's how double buffering is implemented in the client or for each window. Basically, it works much like the Windows Server works with regards to the display frame buffer, that the Windows Server clients, they create 2 bitmaps and they put them in shared memory, and then you're always drawing into one while another one is visible on screen. And then when you're finished drawing, then you just tell the Windows Server, hey, switch to bitmaps. And then the Windows Server goes and switches to bitmaps and then does its own double buffering to the screen. And the purpose of all of that, or the point of all that double buffering, is to avoid flicker and avoid drawing glitches, basically, and make everything smooth, or smooth looking. Yeah, and I should mention that in some cases, some applications turn off this double buffering when they want to manage the buffers themselves, or they want to do like very specific things with the graphics. Then they can turn off the double buffering in the window, which allows them to draw only into a single bitmap all the time, and that is what will be shown on screen. But that requires particular care, so it's double buffering is turned on by default, but if you really want to, you can turn it off, and then that will give you a little bit of a performance edge while you have to mind a whole bunch of other problems in that world. Anyways, yeah. Now, the window manager is an object that's called WS Window Manager, and it lives in the Windows Server process. And the job of the window manager is to keep all the windows, keep track of all the windows, and manage the Z order, and manage all of the rects and the titles and all that stuff. And it tracks which window has focus, and then it figures out like when mouse or keyboard event comes in, like which window is this for, stuff like that. And it also manages the global menu bar, which is the menu at the top of the screen, as well as the system menu, which is the leftmost menu that's always present, no matter which app is running. Yeah, and the fact that the window manager is currently living in the Windows Server process is not really something that I think of as permanent. I would like it to be a separate process. It's just in the Windows Server at the moment because it was convenient to implement everything that way. Going forward, I would like to have enough of an API that you could implement window management outside the Windows Server. But we are definitely not there yet, but it's something I would like to do. And then we have the compositor, which is called the WS compositor, which is a class I wrote fairly recently. And its job is to render the wallpaper and then put all the windows back to front on top of the wallpaper, and then also render the menu bar at the top of the screen, and then do initiate like the page flipping that I talked about, where you tell the graphics card which of the 2 buffers is frontmost and which one is backmost. And the compositor will only run when there is some work to do. So it gets sort of initiated by we kick it whenever we have some work for it to do. Then we either run it right away if we didn't run for a while, or we have a timer that runs runs 60 times per second so that we can throttle this thing at 60 FPS, because we used to not throttle it at 60 FPS, and then certain things like interactive resize would just produce so much compositing work, and we would render like tons and tons of frames that we never even saw on screen, and it was just killing the CPU. So nowadays it's throttled. But yeah, that's the compositor. His job is just to take the window stack and put the wallpaper at the bottom and then draw the window stack on top. So those were basically the main components that I want to talk about there. So let's look a little bit about what's coming next. One thing is threading. I would like to take advantage of threads in the Windows Server. So I would like to have a thread for the compositor so that can run totally independently of all the other code. And then I would also like to have per client threads, or at least try it out to see if it makes sense, so that whenever a client connects to the server, we would spawn a thread, and then that thread does all of the socket communication with that one client, because then we would prevent any one client from monopolizing the Windows server's time, basically, because they would be segregated into threads, and we could do a little bit of controlled management that way. Another thing that I would really like to get to is SIMD optimizations, or basically I would like to use the SSE instruction set for implementing stuff like alpha blending and maybe faster blit with even when there's no alpha. Because currently the alpha blending is done with like regular C++ code, and it's not particularly optimized, and I know that there are plenty of ways that you can do alpha blending with SIMD that would make it like a ton faster. And really, like, while Serenity does support like half transparent terminals, which look very nice, they don't look super nice when you're dragging them around, because redrawing them is kind of expensive because of the alpha blending code. So that's something that it's a very small problem in a way. It's just that I didn't sit down and like figure it out yet. And then, yeah, outer process window manager, I mentioned earlier, that's something I would really like to do. The taskbar currently runs out of process, so the taskbar is implemented using a very early stage of that window management API, that it knows how to sort of like, it can tell which windows exist, and it can tell them to like, hey, go minimize yourself. And that's sort of it. And it can also say like, hey, this should be the active window. So when you click on entry in the taskbar, then you can switch which window is active. But other than that, it doesn't really do much. So I was thinking that we could just extend and keep adding to that API, and eventually we would have enough to implement a window manager, and we could take that out of the Windows server. And there's just all kinds of nice benefits to doing that. The simpler the Windows server could be, the better, basically. And then animations is something I think about. Whenever I minimize a window, I'm always thinking like, well, wouldn't it be nice if it would sort of, even if it would just be like the outline of the window sort of zooming down on the screen a little bit. I currently don't have any support for that. Would be something that would be cool and kind of fun to do, but not go too crazy with it. It should definitely be sticking in the general spirit of Serenity, so it would be something very, tasteful, simple, but also fitting. Yeah. And then snap to foo. I guess I didn't know what to call this one, but like basically if you drag one window close to another one, then if you get close enough, then they would sort of snap together a little bit. Likewise, when you're dragging a window close to the edge of the screen, then it would sort of pop and snap to the edge of the screen. It would be a nice feature to have. And finally, virtual desktops. It would be cool to implement virtual desktops, so you could have like, well, you know what they are, virtual desktops, right? Like you have a screen that's bigger, or a virtual screen that's bigger than the physical screen, and then you could switch which one is active, which part is active. Yeah, and I'm sure there's tons of other stuff to do, and eventually we'll find the time and the inspiration to do all of those things. But yeah, these are just the things I could think of right now. Yeah, so I think that was basically, oh, shit, no, I forgot. Menus, right, menus. Wow, I thought I was at the end there. Menus are managed in the Windows server on behalf of clients. That's right. So every client process can send over a whole bunch of menus to the Windows server. And then whenever any window from that process is active, then that process's menus will also be visible. So it works very much like in the Mac, that like if any window from the terminal app is active, then the terminal app's menu bar is what you see at the top of the screen. Even if the terminal settings is up, then you're still seeing the terminal menu bar. But the system menu is always present, so that's the thing in the top left, same as on the Mac. And that the system menu is managed by the window manager, but all the other menu stuff is managed by the currently active app. Although when I say managed, I don't mean that it's rendered. It's rendered by the Windows server, but what is rendered is controlled by And I should also mention that a menu can either be in the menu bar, or it can be like a standalone pop-up menu. And you can instantiate a menu but not put it in the menu bar, and then you can, wherever you want, basically, you can just say like, hey, show this menu at this coordinate, and then that menu will pop up there. And that's how context menus and yeah, that's how context menus are implemented. Nothing other than context menus, just context menus right now. And now we got to the end. Okay, so if you made it here with me today, then I would like to say thank you for watching. And check out Serenity on GitHub if you haven't already, and also check out my Patreon if you would like to support my work. Of course, it will always be free and open source, but who knows? Maybe you would like to support it anyway. I'm very happy that you came here to check this out. I was trying something different today, making a little presentation. As you can tell, I didn't rehearse or practice this. I just made the presentation and started talking. But I hope it was informative, and I would like to go into greater detail about these systems, but this was just supposed to be a high-level introduction, basically. So thank you for watching, and I will see you next time.